Today we're going to start looking at this idea of a proof by induction. We've seen different types of proofs so far. The most common proof we've seen, of course, is deduction, and you do those with geometry proofs, things like that. You'll recall earlier in the year we did one proof by contradiction as a technique. That's another technique of proof. But this is proof by induction. So the logic behind an induction proof. Okay? So basically, like any proof, it's a series of statements linked using what we call logical connectives. SN's just representing some statement that needs to be proved for all cases. S1 is the first case. It might not necessarily be 1. Sometimes it could be 0. Sometimes it might be 2. But we just say S1 because 1 being the first. So that S1 is sometimes called the base case. You might hear that expression. SK is when we generalise it and we make an assumption. We say, well, actually, we're going to assume it's always true. SK plus 1 then is the next case after the generalised case. And that's what we end up proving. That there is basically mathematical deduction using the language of logic. So we're saying what we need to do in proof by induction, we need the base case and the assumption. Okay, so if we've got those two things, then from that, if we get the k plus 1th case, we can then conclude it's true for all cases. That is the logical symbol for AND. So it's saying, okay, we've got S1 and we've got SK. That arrow to the right means implies. Or another way of saying that is it's the crux of a if-then statement. If I've got this, then I can say this. So it's implication. All right, so the structure of the induction proof. The first thing we do, and by the way, you don't have to write step 1. This is the first thing we do. We'll go and prove that S1, that base case, whatever the first case is. So we'll go and prove that yes, that is indeed true. Then we'll make that assumption that we want to use. So we're actually going to assume, yeah, it's always true. Basically, it's true for the condition of the question. So if we're proving it true for integers, we say, yeah, let's assume it's true for integers. If it's true, we're proving it to be true for even numbers, we say, yeah, let's assume it's true for even numbers. It just depends. Now, if you want to use set notation, then I would say, assume the result is true for n equals k, where k is an element of the positive integers. Now I'll go and prove it true for the case k plus 1. But in there, I'm going to use my assumption. And so when we conclude this step, this is basically the crux of the induction. You must include it. So in your conclusion, what you're basically saying was, well, okay, yeah, I've proved it true for k plus 1. But it only works if my assumption is correct. That's what we're basically saying. We're making the if-then statement sort of in a backwards format. So we're going then if rather than if-then. So we're sort of saying, well, it's true for k plus 1 if it is also true for k. So we're saying, if it's true for k, then it's true for k plus 1. And then we just go and tie it all together, and we've got all those conditions met. We know it's true for the base case, so n equals 1. We now know it's true for k plus 1 if it's true for k. So we've met all the conditions, so we know the result is true by induction. So that's inducing a solution. And if I was going to use set notation for that one, that conclusion, I'd say, oh, well, since the result's true for n equals 1, then it's true. Now that upside down A means for all. So for all n that are positive integers by induction. So let's do one. The first type of ones we're going to look at is series. Now we've got a formula for arithmetic series, we've got a formula for geometric series. But there are lots of other number patterns. Apparently this is the formula if you have a series of adding up odd squares. So 1 squared, 3 squared, 5 squared, we could use this formula. 1/3 n, 2n minus 1, 2n plus 1. So we're going to prove it. So the first thing I'm going to do, first condition I want to meet, true for the first case. So n equals 1. Well, the left-hand side is 1 squared, which is 1. The right-hand side would be 1/3 of 1 times 2 minus 1, which is 1. 2 plus 1, which is 3. 1/3 of 3, and that is also 1. So, yep, The left-hand side does equal the right-hand side, hence it must be true for that first case. So we've got that. Now, oh, and by the way, you wouldn't normally write that, but I'm just noting here. Okay, I've got S1 sorted. Okay. Now I'm going to assume the result's true for n equals k. Basically, it's exactly the same thing that they're asking me to prove, but I'm replacing the letter n with the letter k. So I'm saying, hey, it's going to be true for anything that I put in there. But it will match the conditions, and in this case, it just had to be a positive integer. Now we're going to prove the result's true for k plus 1. It's always good to write down what you're trying to prove. So we'll end up proving that 1 squared plus 3 squared plus 5 squared up to 2k plus 1 squared is a third k plus 1, 2k plus 1, 2k plus 3. So everywhere we see an n, I'm now replacing it with k plus 1. That's what we've got to prove. So here's my proof. Now these series types, they sort of follow the same pattern each time. And so what you can do is, well, that's what I want to prove. I can always rewrite that series as the sum to k terms plus the k plus 1th term. Now again, I wouldn't write that underneath there, but I'm just pointing that out. Now the reason for doing that is because the sum to k terms is our assumption. So I can now substitute in the assumption for all of that 1 squared plus 3 squared plus 5 squared plus ... and so on. We can just put that in. Now I've got an algebraic statement to play with. Now, when you substitute in, it's like any proof. Where'd this come from? How did you do it? In geometry, you'd be saying something like, oh, well, I can say this because alternate angles are equal on parallel lines, or whatever. You explain yourself in a proof. And so you might put down, okay, well, I know that by using the assumption. So by the assumption. I suppose you don't have to. It's kind of obvious it's the assumption. But, you know, it doesn't hurt to write it down. Okay, keep an eye on what we're trying to prove. What we're trying to prove had a common factor of 2k plus 1. So I am not going to expand that out. I'm going to pull it out as a common factor. Why expand it out if later on I'm only going to factorise it back in anyway? Just making too much work for myself. There is another common factor in there which you might miss, and that is 1/3. 1/3 is in both. It means the 2k plus 1, I'll rewrite as 3 lots of 2k plus 1. Okay, so there were the two factors I could get straight away. Why do that? Because what I'm left with is a quadratic, and quadratics are easy to factorise. So let's, so 2k squared plus 5k plus 3, which factorise to be k plus 1, 2k. Is that what we're trying to prove? Outstanding. So we've got our proof. Hence the result is true for k plus 1 if it is true for n equals k. Don't forget that line, it ties it together. So that's the bit that's saying sk implies k plus 1. True for k plus 1. But we can now combine that all together because I know it's true for 1. So if it's true for 1, it must be true for 1 plus 1, which is 2. Oh, now I know it's true for 2. Well, if it's true for 2, it's true for 2 plus 1, which is 3. Yes, true. And if it's true for 3, then you know it's true for 3 plus 1, which is 4. It would take us a long time to list all the positive integers, but there's the induction. Okay, I can now go on that. Let's do another one. Now, this one's using sum notation. So they've given us the general term rather than writing the whole series out. That can save a bit of time too. Well, if you want to get your head around what they're actually asking, then let's rewrite some terms so we can see what it is. So it'd be 1 on 1 times 3 plus 1 on 3 times 5. Notice I'm not saying 1/3 plus 1/15 because I want to pick up what the pattern is. So 1 times 3, 3 times 5, 5 times 7. Okay, consecutive odd numbers we're talking about here in the denominator. Okay, prove it for 1. The left-hand side, that's 1/3. Now, the right-hand side, yes, it's 1 on 2 plus 1. Which is it? Okay, hence it's true for 1. Let's assume it's true. What am I going to assume? There it is written all out in its terms. If you prefer, you could use the sum notation. We're going to prove for the k plus 1th case. So that's what we're trying to prove. Okay, so again, it's a series type. I'll just rewrite it with the second last term in there. Those first up until the second last term. That's our assumption, basically. Substitute the assumption in. Now we've got to play with some algebraic fractions. Algebraic fraction, let's bring them together. 2k plus 1, 2k plus 3 is the common denominator. On top we'll end up with k, 2k plus 3 plus 1. No prizes for guessing what this is about to factorise into. It's 2k squared, but don't write that straight down, that factorised one. It's a proof. You really should be showing these steps. Otherwise, the marker's going to go, did you really know that? Or did you just fudge that? You know? Hey, no. I'll tell you how we know. We're clever. The 2k plus 1s cancel nicely, and voila. True for k plus 1, if it's true for k. Etc., etc., etc. Alrighty, let's play with some of these series types.